Hello, and welcome to the second lesson of Unit 2, differentiability. So just like in Unit 1, where we talked about sort of continuity and what makes a function continuous, there are some functions that are not differentiable at certain points. And so in this lesson, we'll be talking about making that connection between differentiability and continuity, and whether or how to determine if a function is in fact differentiable. So we have a theorem, first theorem from Unit 2, and that is that if f is differentiable at x is equal to c, then f is continuous at x equals c. So note that the converse error here is very much applicable. So in other words, the converse of this statement is not true. So the converse of this statement would be, if f is continuous, then f is differentiable. So continuity does not imply differentiability, but differentiability does imply continuity. And so that is a tool that the AP exam will use a lot to tell you that a function is continuous by telling you that it's differentiable. So if the AP exam or something that I give you states that a function is differentiable for a value of x or on an interval, you can assume that it is continuous on that same interval. So let's look at an example. So we want to show that the continuous function, the absolute value of x minus 2, is not differentiable at 2. So to do that, one of the things we can do is examine the graph. And what you'll see in the summary and what we will discover in this example is that places where there are sharp points on graphs are not differentiable. In other words, really quick changes in the derivative mean that there is a point of non-differentiability. But again, as we can see, that this function is continuous on all real numbers. It's continuous on its entire domain. But our goal here is to show that that point x equals 2 is a point of non-differentiability. So what we want to do is examine what the derivative is doing on the left and on the right. So we're going to look at applying the limit as x approaches 2 from the left and x approaches 2 from the right. So as x approaches 2 from the left, we have that the derivative is f of x minus f of 2 over x minus 2. You'll see that that's that derivative formula that we saw at the end of the last lesson. So this is still a sort of definition of derivative. It's a difference quotient with a limit applied. I'm letting the value of x get really close to 2 from the left side, and I'm looking at the difference in y's over the difference in x's. So f of x we said was x minus 2. F of 2 is 0. And this limit is evaluated to be -1 because the absolute value of x minus 2 is always positive, and the denominator x minus 2 is the same magnitude but can sometimes be negative. So we would say that this limit is -1 because the numerator and the denominator are the same, with the numerator always being positive and the denominator sometimes being negative, especially for values of x that are to the left of 2. Now let's look at this coming from the right side. So the limit as x approaches 2 from the right side, well, the numerator is still always positive because of the absolute value, but the denominator now is also positive because we're considering values of x that are coming from the right side. So x is like 2.01, 2.001, 2.0001. So the denominator is always going to be some positive change in x. So because the magnitudes are the same, we get +1. Since the derivative on the left and on the right are approaching different values, we say that this is not differentiable at x is equal to 2. And again, just as a note, places where functions have sharp points are never differentiable. Let's look at a second example. So in this example, we want to find the value of a and b so that the function f of x is differentiable for all values of x on its domain. So the first thing that we want to do is ensure that the limit exists and is the same from both directions. So here we're just looking at the limit of the function from the left, and from the left we're using the bottom function of that piecewise function. So plugging in 1, we get a plus b. From the right, we're using the top function of the piecewise function, and plugging in 1, we get 2. So what we want is for a plus b to be equal to 2. So we have a little bit of information, but not quite enough to solve for a and b. So the next thing we want to ensure is that the derivative is the same from both directions. So from the left, that's a fairly easy thing to consider because this is the bottom function is just a line that has a slope of a. So its derivative, without having to use the definition of derivative, is just the slope of the line, which in this case is whatever a is. Now from the right, we're going to have to use our definition of derivative, this form of the definition of derivative. And since we're coming from the right, that's going to look like the limit as x approaches 1 from the right of f of 1 minus f of x over 1 minus x. So again, we are sort of considering the point x equals 1, and we're bringing x closer and closer to 1 from the right side. Okay? So we have f of 1 being 1 squared plus 1 minus f of x, which is just x squared plus 1. I'm going to do a little bit of simplification, a little bit of algebra. And we get 1 minus x squared over 1 minus x. Well, that numerator factors, and then I can cancel some factors, 1 minus x and 1 minus x, and I'm left with the limit as x approaches 1 from the right of 1 plus x. So we can see that the top function of this piecewise function has a derivative that approaches 2 from the right side. So what we want, or what we're gathering from this box, is that we want a to equal 2. So from these two equations, or from this system of equations, we can find b to be 0, and so now we have our values of a and b. So one thing that I would like to show you is a Desmos graph, where you can see here that I have the x squared plus 1, the top part of the function graphed. I have the ax plus b, the bottom part of the function graphed. And you can see that I have created 2 sliders for a and b. So we can test points, or we can test out some values for a and b. Okay, so what you can see is as I move b, the line moves up and down. And as I move the slider for a, the line gets steeper or becomes negative. Now let's do something really quick, and let's actually make this a piecewise function and say for x greater than or equal to 1, we want to define that part of the function. And then similarly here, and this way we can really get an idea of what's going on. Okay, so we want to adjust a and b. So as you can see here, if b were -1 and a were 3, I would have a continuous function. These two pieces meet up, and therefore there's no break, there's no jump or gap in the graph, and I have a continuous function. But you should be able to tell, or maybe you can't, but if we zoom in a bit, that the red function is slightly less steep than the blue function. So let's now try our values that we solved for, b being 0 and a being 2. And what you can see now is there's a smooth transition from the slope of the line being 2 to the tangent or the slope of the parabola, the red parabola. So that's just a demonstration of kind of what we were doing in this example by solving for a and b for this piecewise function to create a function that was not only continuous but also differentiable. We were trying to eliminate that sharp point. Okay, so in summary, differentiability guarantees continuity, but continuity does not guarantee differentiability. And a function is never differentiable at points of discontinuity or sharp points. Thanks for watching, and I will see you in the next video.